find the binding energy and the binding energy per nucleon for the nitrogen 14-7 nucleus. Because we're given the mass of the nitrogen atom, so we have to start with the nitrogen atom. If this is the atom, that means it is going to, after we add the binding energy, which is delta M times C squared, it is going to break into, there will be 14 minus 7, 7 neutrons, plus 7 protons, and of course there will also be 7 electrons. To find the mass defect, we need to find the mass for the atom and these ones. And because the composite particles will be heavier than the nitrogen atom, so the delta M would equal to the heavier part minus the lighter part. So I'm going to do this 7 neutrons, 7 times the mass of a neutron, 1.008664, and I'm just going to leave the U out and then put it in later, plus 7 protons, 7 times 1.00727665, plus 7 electrons, 7 times 0.0005486, and then minus the atom's mass, which is 14.0030740, and this is in unit U. So let's do the calculation. It is very important that at this step we do not round any of the numbers, because the numbers are really close. If we round the numbers, we may end up having 0 for the mass defect. So I get 0.112356 U. This means the binding energy would equal to the 0.112356 U would be 931 mega eV over C squared. So it's 931 mega eV over C squared. And since the binding energy is delta M times C squared, the C squared will cancel over here. Now we can round. But before we find this number here, we cannot round any of these numbers over here. Now we can round, and then we'll get 104.6 mega EVs. And that's the total binding energy. If I want the binding energy per nucleon, then I'll have to divide the total binding energy by the number of nucleons, and that will be 104.6 mega EVs divided by the number of nucleons will be 14. And this will give us 7.47 mega EVs. Sometimes we may be given the mass of hydrogen 1,1 atom instead of the mass of a proton and the mass of an electron. Because a hydrogen 1,1 atom has 1 proton and no neutron and 1 electron, we can use 7 hydrogen 1,1 atoms to substitute for the 7 protons and the 7 electrons. Therefore, this can actually make our calculations a bit simpler. So on this side, it's going to be 7 neutrons plus 7 H11s. We're using a H11 to substitute for a proton and an electron. So the delta M is going to be still the heavier side minus the lighter side. So 7 neutrons, 1.008664 U, plus 7 hydrogen 1,1s. 7 times 1.007825 minus the nitrogen atom, which is 14.0030740, and then of course I have to remember my u over there, and so this will give me 0.1123553 u, and therefore the total binding energy would be the delta M times C squared. Now the delta M is 0.1123553. U is 931 mega eV over C squared. So if I multiply this by C squared, again the C squared would cancel. So this will give me also 104.6 mega EVs. And then of course we divide by 14, we can get the binding energy per nucleon. By the way, in both methods we ignored one thing, the binding energy between the electrons and the atom. There is actually binding energy for the electrons to be bound to the nitrogen atom and the binding energy for the electrons to be bound to the hydrogen atom. But the binding energy for electrons is much smaller compared to the nuclear binding energy. So we can just ignore the binding energy for the electrons. The binding energy for the electrons involves electromagnetic force, but the nuclear binding energy involves much stronger nuclear strong force.